Before we begin, I would like everyone to press hand raise to confirm that they are hearing my voice in a clear manner. Very good. Today's topic is transformer differential protection, testing with SMRT and the Freja 500 series. My name is Ali Hussein. I am an application and sales engineer in Megger, Middle East. I will be your presenter today, and we'll go through all the question and answer session at the end. Please remember that during any time at the presentation, you can ask any question in the question panel to the right of your screen. The question asked will be answered at the end of the Q&A session. Okay, let's get started. Our agenda today is basically I'm going to give a small introduction about differential protection in general, then specifically about the transformer differential, what things we need to consider in transformer differential. Then we are going to talk about the transformer differential different tests, and they are mentioned here as stability test, pickup test, timing, harmonic, and last, the bias slope test. We'll go talk about each one in details, but not in the theoretical way, where how this protection or how these tests done in details, but how to set up them using the RTMS software. The software supporting the SMRT and Freja 500 series. And we'll see how we can do them for different types of relays and different also configurations. This session today will be heavily based on a practical session, not just a theoretical one. So I hope you enjoy it very well. As an introduction, differential protection is based on the KCL law, which is a basic law when you are studying electrical engineering everywhere. The KCL law, or what's called Kirchhoff's current law, states that when currents enter a node, they must come out. So the whole summation of current entering a place should equal to be 0. So what comes in should goes out. And this principle is what driving the differential protection in general. And differential protection can be applied in different assets like transformers, transmission lines and cables. If you have generators, motors, bus bar. And the idea of it is similar to what's stated in the graph to the left here. When I have a protected object, it doesn't matter what the protected object is, a line, transformer, generator, and I have sides of currents going to this protected objects. The summation of these sides under normal condition should be equal to a value near 0. And also the summation of these currents going to this protected object, we call it the differential current, where we use it as a criteria to state whether our protected object is in healthy condition or is in non-healthy condition, like a faulty condition, or it has an abnormal condition. Thus, if there is a path for the current outside of these measuring zones, usually stated by current transformers, CTs, if there is a leakage to the ground or between the two phases or whatever, the differential current will not be equal to 0. Thus, the current is flowing into a place or direction that is not normal for it, meaning you have basically a fault, and then a trip will occur. This type of or principle of protection give you 100% selectivity on your protected area, and thus allow you to give a very fast operation in case of a fault. Usually this operation is instantaneous. It's very fast, 0 millisecond. Now, the downfall or the cons of using differential protection is that it requires too much cost compared to other protection principles, but nonetheless, this cost worth the trouble of doing it. Now, this is differential protection in general, but what about transformer differential? When you have a transformer as your protected object, let's take, for example, this transformer. It's a vector group of DY1. It have a high HV side of 500 kV and LV side of 230 kV. And the rated power of this transformer is equal Apologize everyone, apparently my screen is not shared. We'll start over again. My apologies about this confusion. Apparently my screen was not shared at the beginning of the webinar automatically. So we will start again with the introduction. I just want to mention to you that you can ask any question during the webinar at any given time, and this question will be answered at the end of the webinar. For our agenda today, we will talk briefly about an introduction to differential protection in general, then specifically for transformer differential. After that, we will talk about each specific test that we do for transformer differential protection, how we can achieve it, and how we can do it with the RTMS software, which is supporting the SMRT and Freja 500 series. Our session today heavily will be based on a practical session rather than a theoretical one. So because of the time limits, we cannot go further into differential protection, as it might require us the whole day explaining all the details. So differential protection in general is based on Kirchhoff's current law, or what we call KCL. It's a very basic rule and fundamental rule we used in electrical engineering that states that whenever a current enters a place or a protected object or anode, it should come out from the other sides. So when I have a protected object here that it's been fed current from 3 sides, the summation of these 3 sides of these 3 currents should equal to 0. Now, the summation of these currents, or all the sides that I am measuring here using current transformers, should equal to me a criteria on operating current. We call it I differential. That we use this criteria to define whether we have a healthy condition or non-healthy condition, a faulty condition or not. In general, when everything is working fine, there is no leakages or faults or abnormalities, the differential current or the summation of all these sides should be equal to 0. When the current does not equal to 0, it exceed a certain value, we declare that there is an abnormal condition, usually a fault inside my protected object, and thus isolation or trip to this protected object will happen or occur. Now, differential protection in general can be applied to transformers, lines, generators, bus bar efficiently, and it is a very good protection principle, or you can say even the best protection principle that you can use to give you 100% selectivity in your protected object. The reason for that is because your protected zone will be starting from your measuring points or your CTs, current transformers. And because you have 100% selectivity, you are allowed to put your operation time to be very fast, usually instantaneously. Now, this is differential protection in general, but what about transformer differential protection? In transformer differential protection, there are a number of factors that we need to consider before applying the principle itself. When you are having a transformer, for example, in this example, I have a transformer which have an HV side of 500 kV to LV side of 230 kV and a power rating of 1000 MVA. When you apply a differential protection to it, you will put CT at the HV side or CT collection for each phase and a CT collection on the LV side to protect this transformer and start your zone. When you put this configuration, you will find out that the rated current on your HV side and LV side is different. And the reason for that is because of the transformation ratio between the HV and the LV. So you will have to use different CT ratios at each end. For example, at the LV here, I have 2000 ampere to 1 CT ratio. And in the HV, I have 4000 to 1 ampere. And when I convert the nominal currents of the primary to secondary, I will have different values under normal condition. They will be different in magnitude and also in phase. So if I compare my I phase A at the HV side, it's 0.577 ampere in this configuration example. And at the LV side, it's 0.628 ampere. With a degree, should be 180 degree, means what comes in goes out. But what you can see here is 210 degree. The reason for that is because I have a vector group and also my conversion from primary to secondary, since I have changed the CT ratios at the different ends, it will be also mismatched. So the differential current here, when I under normal condition, there is no fault, it will not be equal to 0, and thus creating problems for me. To avoid these problems, most relays nowadays, numerical relays mainly, they have compensation methods to compensate for these factors. And these compensation methods include CT mismatching factors, vector group. When you have a vector group in your transformer indicating a phase shift between the HV and the LV side, this phase shift will be compensated automatically using specific matrices for each relay manufacturer, and also something we call single phase pickup factor. This is when you have a single phase fault outside your zone. There are some certain compensation needed to be added to protect against mal operations. Now, all these things are related to your protection relay. You just need to know that they exist and why you need to input all this information to avoid this. The SMRT test kit and the Freja 500 software are compensating for these factors automatically once they know the related information to them. So I'm not going too much in detail about this information. If you want to know more details about that, I urge you to contact me on my email. I can provide you more information about that. The testing for differential protection, usually there are 5 tests required to be able to completely test a transformer differential protection. These 5 tests as follow. First, we have a stability test where we test the stability of the relay during an through fault or what we call outside of the zone fault, to see that it will not have any mal operation or unstable values during this fault, or even during normal operation condition. When there is no fault, it should be stable and does not have any mal operation when you have full load or a slight overload as well. Then there are pickup tests where we test the start of operation according to the differential current. Also, we will test the trip times. I know I have mentioned that the operation of differential protection is usually instantaneous, but in real life, there is no such thing as instantaneous. There will always be a slight delay. We will test that and see how much is that delay, and is it acceptable or not acceptable according to my requirement. Then we will do some harmonic restraints. There are some harmonic contact that used for specific purposes. We'll see how this test conducted using the SMRT, and also why do we need these harmonic restraint in the first place. And the last but not least is the bias characteristic slope. We'll see why do we need this bias characteristic slope and how do we test it using the RTMS. So, as I mentioned to you earlier, our session will be heavily a practical one. I have a setup here with me and connected to a camera that I will show you the setup shortly. And this setup, when you are testing a transformer differential, please note that your test kit needs to be able to supply 6 current simultaneously to be able to completely test a transformer differential. So when you have a Freja 543 or SMRT 43 or even SMRT 1, where you have only 3 currents output available for you, you will not be able to complete this test using that test kit alone. You might want to use a different test kit along with it to do this test as well. So it is recommended, or actually required, to have either Freja 546 or 549 or SMRT 46 or 410 to be able to test a transformer differential to their fully. And the connection is basically very simple. I will connect the first 3 channels to the HV side, and the first and the 4, 5, 6 channel to the LV side, or as I require. There is no problem about this. I can connect or interchange the windings. There is no issue. It's easily changeable in the software. And also, I need to take a trip command from my relay under test to be able to complete or automate these tests automatically. In our practical example today, I have a relay REG. It's a generator protection relay. But in this generator protection relay, there is a transformer differential function that we can utilize to do full testing as we require. The following setting on our relay is as shown in the screen. I have a transformer that have an HV side of 500 kV and LV side of 230 kV and a power rating of 1000 MVA with a vector group of dy1. My current transformers is 2000 to 1 at the HV side and 4000 to 1 at the LV side. The differential setting or the differential protection settings, we will go through those as we go through the test, especially the slope test, where we'll use most of these settings in. So let's go to our screen here or camera to show you the setup. I have the relay here with me, ready and connected to my Freja system here. If you are using SMRT system, it's very similar to the Freja system. Only thing that you will be missing is the touch screen in front. You will be using the laptop, using the exact software as I am using in the touch screen. So the first test I'm going to do or I'm going to talk about is the setting page. There is a setting page that I need to fill in order to complete all these 5 mentioned tests. And this settings page consists of 2 sections. I have the transformer information section, where I put the voltage levels, kVA, vector group, CT ratios, and the single phase pickup factors. And then the protective device information. This is the information for the protection system inside my relay. What is my pickup times, slope, configuration. So in order to be able to access this page and the RTMS software, zoom in. I will click on the test screens, and under differential, I have 3 types: T for transformer, G for generator, and M for motor. I will click on T, and in the setting page here, the blue button, if I click on it, it will take me to this setting page. For our first test, which is the stabilization test, I will not need to fill all this information. I will only need to fill the transformer section information, and then I can begin the test and see what that test will give me and how can I analyze the result at the end of this test. So let's go back to the presentation and go to the stabilization test. The stabilization test basically confirms for me the following things: that my ratios and my mismatching factors and my vector group inside my transformer or my protection relay is set correctly. So when I inject a through fault or a fault outside my zone, the differential current should be equal to 0. And that's what we will do. So in order to be applying, or what I need to apply this test is two things. I need to put the transformer information, CT ratio, vector group, voltages, and power ratings, and also how much through fault current level in percentage. I can put this percentage as I like. I want it 50%, 100%, 200% means 2 times my nominal current, 500%. I can select it in this slot here, the through fault current field. So let's go back to my camera here. I have already take the liberty of putting the transformer information, 500 to 230 kV transformer at 1000 MVA, and my CT ratios is 2000 to 1 and 4000 to 1 ampere, and my vector group is DY1. If I want to change it, for example, I just can click on the vector group and I select which configuration I have from a large number of configuration. If I select that, it will ask me to put or compute the single phase pickup factors. We will talk about this shortly afterwards in the pickup tests. So I click OK. And also my through fault current is defaulted at 100%. If I want more, I can click here and change the value as I like. Once I finish, I click on the right or the left tick mark. And it will take me to the stabilization test screen. In this screen, the Freja or SMRT will be injecting these currents in a secondary, and correspondingly in a primary, this current will be equaling to this much, according to the setting I have set. And once I do this test, I click play, I should be reading the measured values inside my relay. So I will click start. The test kit will be start injecting values into my relay here. If I zoom in on the relay, I should be reading the values. I'll go to the test section in this relay. In other relays, it might be in somewhere else. Function status, differential protection, transformer differential for 2 windings. And at the end of the page, you'll find here the values for the differential currents. Now, if you can see here, the values is 11, 9, and 5. These values in primary. So if I compare them to my CT ratio, they are almost 0. Now, since I get these values, I'll go back to my Freja. I can enter these values into my table here, indicating that I have recorded the values, and I can click finish to stop this test. And you can see here the I bias value, which is the value of the measured injected current in primary, is 1000 in primary, while the differential current is almost 0. Differential current is almost 0 at the 3 phases here, which indicating to me that the relay is stabilized during a through fault or even normal operation condition when I inject these values to it. Now, as you can see, I did not need to do a lot of calculation. I just needed to put some information about my transformer, CTs, and my vector group, and all of this. All of these values have been calculated automatically for me. Now, the second test I'm going to do is pickup test. Now, when you want to do these tests, it's better always to start with a stabilization test. It's not only going to verify that your relay is stabilized, but also going to verify that the setting that you have entered in the RTMS is also correct to be able to do all the other tests. So the pickup test basically test for me the start of pickup. Is it according to the acceptable tolerance or not? And also will test for me is the single phase pickup factors. Now, this single phase pickup factors, I avoid talking about them because they might introduce some complexity that I want to avoid. And in order to also make it simpler for you when you want to do testing, in the handout section on the panel in front of you, there is a file attached that you can download. It have a differential relay setting help that help you define what is your single phase pickup factors in the HV and LV windings according to different vector group arrangements. And it's not only in general for any relay to be used, but also specified for each manufacturer. For example, manufacturer A, B, C, each one have their own relay available, and how much is the single phase pickup factor according to your vector group. So I need to put these single phase pickup factors, and also I need all the transformer information, obviously. And the next setting I need to input is the pickup setting. It's available here under the protection section, and the current tolerance. Now, this current tolerance, usually you will acquire it from the reference manual of your protective device. This tolerance, once we do testing, the error in this tolerance should not be exceeded, as when we do testing, it will automatically give you pass or fail according to this error value. So let's go back to our test screen and put these pickup factors. They are 1.73 for the HV winding and 1.5 for the LV winding. My pickup value is 0.3 according to my setting, and my current tolerance is 2% according to the relay manual. So I click OK. Now to go to the pickup test, I will click on this page or this icon here, and I will go to pickup test. In this pickup test, I will be doing it for the LV winding and also for the HV winding as well. So I can start on each individual one if I want, or I can click double play, run all pickup tests. Of course, I need to define what is my contact that I'm using, which is binary input 1 in this case. If the single phase factor did not give you a correct value, or if the single phase tests did not give you a correct values, please check your single phase pickup factor, as mainly the issue will be from that one. So here I'm having an error of 1%, which is to some degree is acceptable. Also, we can see the setup. Once we get a trip, the LED will run. As the LED run, it went to the next setup, as you can see. Now, for the three-phase value, we'll see it differently than the single-phase value. And the reason for that is because of something called zero sequence elimination, or it's related to this single-phase pickup factor. Now the pickup test has been done. So you can see all of the result is within our tolerance, meaning we have a very good accuracy inside our protective device. Also, as I mentioned for you, the three-phase values was different than the single-phase value, and that was related to the single-phase or zero sequence elimination for the single-phase faults. So the next test is the trip time tests. And this trip time, we will check how much time delay the relay takes to operate. Now this relay is an instantaneous operation, 0 millisecond. It should be 0 millisecond, but when you actually see the trip time, it will not be actually 0 millisecond. It will have 20 to 30 millisecond delay, and that's very normal because the relay have algorithm. It takes one or more cycle to do all the calculation it needs to decide whether you have a fault or not, which increase its reliability under any noises or transients in the system. So the setting I need for this test is the trip time setting and the trip time tolerance as well. And also I need to make sure that my fault duration during the testing is enough to trip the relay. So if in case if I have an intended time delay, I need to change this field of fault duration to be above that trip time delay to be able to satisfy the requirement of the relay for testing. One thing I need to mention is don't try to do this test before the stabilization or the pickup test, because if you have succeeded in doing this other test you will not have any problems in doing this test as well. So let's go back to our setting page and add these values. So my trip time is 50 milliseconds. I cannot keep it 0 because 0 instantaneously is not something an actual value. So I will keep it 50 as something we are accustomed to. As for the tolerances is 25, I believe 25 milliseconds, and as a percentage, let's keep it 5%. The fault duration is 500 milliseconds, 10 times my nominal trip time, so it's normal. I don't have to change that at all. Click OK. Go to the test pages, timing test, and make sure my contact is number 1. And I click start. And click start all actually. You can see very fast. And the trip time is almost 33 to 31 millisecond each time, which is according to our nominal values. Now, the next test is the harmonic restraint test. These I did not talk about them in details, but there are some conditions like inrush currents. This is especially when you are starting to energize a transformer. A huge current will be drawn inside the transformer itself, not outside. So the differential might consider this current as fault. And this current, the inrush current, we are using it, or the transformer is using it to magnetize its core. This current have a heavily a second waveform or second harmonic waveform inside of it. So they are using a method of second harmonic restraints to detect this inrush current condition and block it for some time. Also, another condition called overexcitation or overvoltage, they are using fifth harmonic restraint to block the differential protection for some duration. And these conditions are applied everywhere, almost everywhere, in most of differential protection devices nowadays. To be able to test them, you will need to fill these following fields: the second harmonic content field, and the nth harmonic. The nth harmonic, usually you will choose it as the fifth or the third harmonic. Usually it's the fifth harmonic, because the third harmonics are eliminated in delta connections or delta vector groups, so you will not find it easily there. So that's why they are usually using fifth harmonic. And also you need to put how much tolerance you need and what is the ramping mode for this test. Usually the ramping mode, we will select it to be ramp to operate. So we don't have to change the contact status when we do testing. So let's input these values. For the second harmonic, I have 12%. For the fifth harmonic, I have 40%. Take to my setting page. For the second harmonic, I will put it 12%. For the fifth harmonic, here I have to select the fifth. I say click on this, select the fifth, and I'm telling him 40%. This is according to the setting inside the relay. And the ramp mode, if I click on it, it will change. I will select ramp to operate. Means go from the restraint region to the operation region. And for the tolerance, it's usually 5%, even less, I believe, for this relay, but let's say it's 5% for us now. So I put all these settings, go back to the test page again, select the harmonic, second harmonic block test. and I will click play on harmonic test. So it will do it for each individual phase, and then for the 3-phase in total. It will do it for winding 1 and winding 2 to check the ability of each CT inputs, the LV side and the HV side, to measure the harmonic contents, the second harmonic contents in my waveform. So as you can see, I am ramping down to the trip region. Above 12%, I should get block. Below 10%, 12%, I should get a trip signal, which indicates that the setting is actually applied and can be measured by the relay as well. So as you can see here, we have done the second harmonic block test, and all the results are within the nominal values. If I go now also to the nth harmonic, which is the 5th one, where we have chosen, we can also do the test as well for all the winding. In this test, we are not doing any ramping, we're just doing a shot before and after the limit to check that it's operating or not. The last test available is the slope test, where we test the slope. In this test, we will talk in more details about how to configure the slope as a setting and how to use it for different also manufacturers and curves types. Okay. So now we have finished all the harmonic contents and all the other tests. The last test we are going to do is the slope test. And the slope test, it is very importantly to know how your slope or how your differential relay works. All the previous tests they somewhat will be very similar from one manufacturer to other, from different manufacturer. They will be almost very similar to each other. But for the slope test here, a lot of difference will be happening between different manufacturers. That's why we at Megger have provided you all the needs to be able to test almost all relays as you need. And the slope test, or the bias slope, basically what we are doing is we are taking two quantities and comparing with them with each other under some types of a slope to avoid the issues like on-loop tab changer when I have a different tab in my transformer than the nominal one, which I have done all my calculation on. This tab should not introduce any differential current to me. And also for magnetizing currents, when I have magnetizing current going to my transformer, or excitation current, some might call it, also to eliminate this condition from generating a trip for me. And last but not least is when I have a CT saturation. Now, as I mentioned, in each side, the CT will be different. This 2000 to 1, this is 4000 to 1. So definitely their saturation characteristic will be different. So I need to account for that as well. So the differential current in most relays will be calculated as this, summing of the all the currents. In our case, we have two windings, so winding 1, winding 2, an angular summing as well, or a vectorial summing, not just a magnitude. But for the I bias, the second quantity I need to compare here, there is a lot of differences between manufacturers. Some of them is using the first equation here, IB plus IS as magnitudes. Some of them using the same equation divided by 2. Some of them divided by 3. Some of them is using max, IB or IS. Some of them using minimum between the IB or I primary and I secondary. Now, it doesn't matter what the equation is. You just need to know it and select it when you want to do testing. And this equation, based on it, I bias value will be calculated for our REG or RET even 670 relays. The slope is calculated as the picture showing in front of you here. And the I biased equation used is the max IB or IS. Now, if you can see this slope, it might require a lot of calculation or something like that to input this data, but that's not true with the RTMS software. We have an easy way for you to do that. You just have to select the relay and put the setting related to the slope inside the corrected values, and you will be ready to go if you want. So if I go to my setting page again, the information about the slope is available here. If I want to enter them manually, I can do that here, or I can click on this small library picture. It will open to me a lot of very famous relays, ABB RET670, Siemens 7UT, MyCom B63 and B64 as well, SER relays. For our relay, the REG is very similar to the RET670. So I will click on the RET670. It will open a window for me, also showing how the characteristic is addressed and telling me to enter the data as I have it in my relay. And it will automatically input to me there. So I will put this data here for the IED is 0.3. The unrestrained value is 7.5. Section 1 is 1.25. slope section 1 is 40%, and section 2 is a 3, and slope section 3 is 80%. Also here mentioning me if you have any second harmonic contact, which is 12, and this one is 40 for the fifth. Also the pickup factor, it's also putting them for you here to choose depending on if you have an even or odd vector group, you can directly put them depend on your vector group. So here I have 1.73, and the second one is 1.5. Click OK. It will enter all the data for me. It will change and it directly choose the right formula for the I-bias equation here directly for me. So I click OK. And now go to the last test, which is the slope test or the characteristic. I can do it either as a slope, which will do a search for me, or as shots if I don't want to take a long time. So I will do the slope test. Now it will open for me the slope test. It will do it only as a 3-phase test, since in all cases we are just testing the slope, not the all combination. In the near future, maybe it will be added to be able to do with all the configuration, like face-to-face and even single phase as well. So I will add values here. So I can click on the curve and it will add the values for me. And once I add this value, I can even change how much is the value I want. So I can make this one 1, for example. This one 2. And you can add as much want as you like. Just to test all the curves that we have. And let me add the fourth point as well on the second curve here. Click, and now slope test. Now, in this test, it's not going to do an actual ramp. It will do a pulse ramp for this test to test this. As we can see here, my tolerance for the slope is a little bit giving me some value failure here. For example, this is 2%, slightly above my actual value that I have set, which is 2%. And this is 3%, also slightly higher, which I can accept them, no problem with that. Now, if I did this is just a slope test. If you want to do shots, you also have the option to do that by selecting the second test as well. And I can click directly on the share to add shots. So if you are here, it will do only a shot above and below. It will give you either trip or no trip, depends on the values that you have. Click run all. It will be very fast, much faster than doing the normal slope test. Pass here meaning it did not trip for the second point here. The value is below the line, should not trip. It's the relay did not trip for that. And that will be all for all the tests for transformer differential. Thank you very much for joining us today. My email address here, in case you have any details you want to know, you can send them here to me and I will answer them. I will be gladly answering them for you. Now we will go to the question session. I have a lot of questions here for me. I'll try to answer as much as possible. The first question I have here is asking about how can we make configuration of a CT for primary and secondary in case of a DY group. Now, this question depends on your protected device. If you have a numerical relay, most of the numerical relays are able to compensate for this phase shift between the delta and the Y automatically for you without the need of doing a special connection to your CTs. You just connect your CTs as Y configuration in the HV side and Y configuration in the LV side, and the relay will do all the compensation required and needed automatically for you. But in case you are dealing with an old electromechanical relays, in that case, usually you will flip. In the delta side, you will connect the Y connection, and in the Y side of the transformer, power transformer, you will connect a delta CT connection for the measurement. We also support these two. When you are doing that, we can allow you to put a setting for that in the RTMS screen as well. But it's better to test before these interposing CTs, as we call them, automatically, and they should measure or even test them with the protection system in complete shot as well. Another question I have is, can we do testing using Sverker 900? Now, if you are doing, for example, generator differential or motor differential, yes, Sverker 900 will be sufficient to do that testing, provided that you test each phase separately. But unfortunately, for transformer differential, it will be difficult to do that, or not possible to do that with most of the configuration or vector group configuration, as you will be required to inject 6 currents in all windings at the same time to get the correct measurement value from, or correct operation from the protection relay. Another question I'm having here is, what is interposing CTs? Interposing CTs, as I mentioned earlier, they are used in case of an electromechanical relays, where these electromechanical relays cannot compensate for the mismatching in CTs from the HV side and the LV side. We use some types of interposing CTs to compensate for these factors. Also, another question from the same person asking, what is the single phase pickup factor? Now, to answer you this in detail, please write me an email and I will send you a paper and some explanation explaining this in more details for you, as it is difficult to explain it right here in front or just by talking. It requires some measurement or diagrams to explain that easier for you. Another question I have here is what is the importance to verify the vector group, and what is the difference result in each vector group? Very good question. And verifying this vector group is usually done in the stabilization test. This stabilization test will inject a through fault for you across the 6 windings, the HV and the LV sides, and make sure that the values according, or the setting inside the relay that compensating for everything is similar to the setting of my protected object, which is my transformer. Verifying this will not only give you indication that the relay is stable, but also when you do all the next tests, the pickup, the timing, the slope, even the harmonic tests, you will not get valid results. And getting the keyword here is a valid result. You might get them pass, but they are invalid results, meaning they are not done correctly until you have passed the stabilization test correctly. It is very, very important to do this. Another question I have here is also asking about the zero sequence elimination and the single phase pickup factor. I urge you again to send me an email so I can discuss this further with you. Question coming also about restrict. Have a neutral and see if there is a slight leakage in your neutral to one of the windings. That's the sole benefit of that protection principle. It really covers maybe 1% or 2% of the possible faults that might happen inside transformers. Another question I'm having here is what is the effect of CT error in the stability of the differential relay? That's a very good question. Thank you very much for asking that. The CT error or protection CTs usually during fault will have a normal error of 5% or 10% maybe. Now, this error, when I'm having a through fault, meaning a fault not inside my transformer, but alongside my system, maybe an adjacent transmission line or different place, this fault current will go through my transformer and through the CTs in the HV and the LV windings. Now, since I'm having different CT ratios, definitely I will have slightly different saturation error. Now, this saturation error, if I did not account for them in the slope test, this fault might give me a false or mal-operation, we call it. And thus, the stability of my relay is compromised. Regarding the video or the recording of this webinar, it will be available for you. At the end, it will be sent automatically for you after 1 day of this webinar end. As for the presentation, unfortunately, I cannot provide you with that. If you want more information, you can contact me. I can help you in more details. It's look like we are out of questions. If you think you have anything else, as I remind you, feel free to contact us anytime at the provided email address. Thank you all for attending. Please have a great day and goodbye.